Hello everyone, this is Dr. Lennon, and this is a video lecture to show a few more examples of implicit differentiation. So we talked about that on Monday, and remember this is the idea that in some formulas that are not necessarily functions, it might be hard to necessarily solve for y, but there's often still a way to compute the notion of the derivative, that is the formula that gives the slope for all the tangent lines on a smooth curve. And that is to think of y as an implicit function of x. So basically what that amounts to is every time we take the derivative of something involving y, we multiply by y prime via the chain rule. And that's why we think of y as an implicit function of x. And then if we can solve for y prime, which is usually easier to do than solving for y itself, then we have a formula for the derivative. So that allows us to find tangent lines and find equations of tangent lines and understand the derivative for things that are not necessarily functions. And sometimes even for functions that gives us a bit of an easier way to do things. So we may see that in the future. But let's continue. So let's just go through 3 quick examples, and then I'll give you 2 to work on that we will go back over on Friday in class when I return. So the first one is to find the derivative, so that is y prime, for the equation of the hyperbola above, given, x squared minus y squared equals 1. So we're treating x just as normal, so when we take the derivative of it, we get 2x. But then when we take the derivative of y, well, normally it would be 2y, but since we're taking the derivative of something that involves a y, from the chain rule, we multiply by a y prime. And then the derivative of the right-hand side, 1, is just equal to 0. The derivative of any constant on its own without being multiplied by a variable is equal to 0. Okay, so then we add 2y, y prime to the other side, and we're just going to divide by 2y on both sides to isolate y prime. So we divide by 2y, and we get y prime is equal to 2x divided by 2y, and we can cancel the 2's, so we end up with y prime is equal to x over y, and that is your derivative formula for the hyperbola here. So notice the derivative formula does involve both variables, so if you want to find the slope of a tangent line or something like that, you're going to actually have to know the point before you plug it in that you're looking to find that tangent line slope for. Okay, so example number 2, a bit more interesting because of that middle term, x squared y. We're going to require a product rule, so we're trying to differentiate here. So the first term, x cubed, it has derivative 3x squared, but the middle term, we need a product rule. So basically, we split up the factors into x squared is one factor and y is the other factor. So if you write that out, we would have u equals x squared and v equals y. So u prime would be 2x and v prime would be y prime, right? Because the derivative of y would be 1, but then because we're thinking of y as an implicit function of x, we also multiply by y prime. So multiplying diagonally and adding, you would have 2xy plus x squared y prime. And then the derivative of 4y squared would be 8y times y prime. And then the right-hand side, the derivative of 6 would be 0. So we have 2 terms that have a y prime on them in this case. So what we're going to do is we're going to keep the y prime terms on the left, and we're going to subtract 3x squared and also subtract 2xy. So when we do that, what we're going to be able to do is factor the y prime on the left-hand side. So factoring y prime, we'll have quantity x squared plus 8 on the left, and we're just going to leave the right side as is, minus 3x squared minus 2xy. And then once you have y prime isolated like that, you can go ahead and divide. And we have our formula for y prime, minus 3x squared minus 2xy, divided by the quantity x squared plus 8y. So that's another one where we have the implicit differentiation, but we also have a product rule available to us. And on one of the examples that I'll give you for homework, there's going to be a chain rule involved with a exponential function. Actually, a chain rule and a product rule. So that'll be some fun for you to go ahead and look at. And we'll go over that on Friday. So the last one is an application where we want to find the tangent line of x squared plus xy plus y squared equals 3 at the specific point 1, 1. So we're going to use implicit on the left, and it's pretty similar. We're going to get a product rule in the middle. So taking the derivative, we see that we get 2x, and then, okay, the derivative of x is 1, so 1 times y, plus x times the derivative of y, which we're writing down as y prime because we're using implicit. And then taking the derivative of y squared is 2y times y prime. And the right-hand side, the derivative of 3 is equal to 0. So same game, subtract 2x and subtract y. And then on the left-hand side, we have xy prime plus 2y y prime. So we can factor a y prime out. And we'll have x plus 2y times y prime, which is the quantity we'll divide by. Okay, so that's our value of the derivative. Now what we can do is we can plug in our point, and if we plug in our point, 1 for x and 1 for y, that will give us the value of the slope of our tangent line. So once we have the slope, you can plug in the point 1, 1 to find the value of the y-intercept. So that's what we're going to do next. So the slope, negative 2 times 1 minus 1 divided by 1 plus 2 times 1 gives you negative 3 divided by 3, and that simplifies to negative 1. So the next thing we're trying to do is find the equation of the tangent line. So remember that the slope is 1. Oh, so that's a typo. The slope should be negative 1 there. So when I post the this PowerPoint on under the course documents, I'll fix that. But I believe the rest of the problem should be okay. So just note the slope that should say minus 1 there. So yeah, so I have it correct in the next step. Y should equal minus x plus b. So then we're going to plug in our point 1, 1. So if you plug in 1, we get 1 equals negative 1 plus b. Add 1 to both sides, and we see that our y-intercept is equal to 2. So that's the equation of our tangent line, and I actually went ahead and graphed that for us on Desmos. So let's see. Okay, so here's our curve. X squared plus y plus xy plus, oh, so I did plus y cubed. That should have been y squared, huh? Y squared equals 3, so this is actually an ellipse. You could see that this is an ellipse by factoring, or by completing the square, technically. But then we have that point of tangency right there, 1, 1. So our line is y equals minus x plus 2. So we have an ellipse, then we have the equation of the tangent line, and it's tangent exactly at the point that we thought it would be, so that's good. All right, so let's go ahead and view this in full screen again. So full screen mode. And let's look, okay, so that's our tangent line, y equals minus x plus 2 that we just saw. Okay, so I have 2 of you to practice for homework. So the first one is just find the value of y prime, differentiate. So we have e raised to the x squared times y. So basically you have a chain rule. So you're going to want to think of the inside function as x squared y, and the outside function is e to the t. And then actually your inside function x squared y, you also have a product rule. The right-hand side is pretty straightforward. The derivative of the right-hand side is just 1 plus y prime. So the left-hand side is the tricky bit. And, you know, you may have to do some collecting and factoring of y primes like we did in examples, 2 and 3. The second one, find the equation of a tangent line of the curve x to the 2/3 plus y to the 2/3 equals 4 at negative 3 square root 3, comma 1. So, I mean, the curve here actually doesn't have anything complicated. No chain rules, no product rules, no quotient rules. You just have to use some basic shortcuts and then use the fact that you can plug in the point to find the slope, and then also plug in the point to find the y-intercept once you know the value of the slope. So maybe the shortcuts seem a little difficult because we have fractional powers, but they really shouldn't be. For instance, you're just say the derivative of x to the 2/3, that's going to be 2/3 x to the negative 1/3. So nothing fancy there. Then the same thing for y, but you just multiply by y prime, and then you solve for y prime. Again, we'll take these 2 questions and we will go over them at the beginning of class on Friday when I return. If you have any questions, I should be able to email you back on Thursday. This is from, I believe, section 3.5. So go ahead and have a look at some of the other examples in the book if you finish these up rather quickly. Yeah, this is Dr. Lennon signing off.